in order for us to find out the value of the axial force inside of our partial cone, we're going to have to dust off a formula that we may have encountered in the past. But let's draw our little free body diagram. We've got the weight of that little chunk of cone, and that is our determined height of x. And then we've already figured out what the radius is. That's our r of x right there. And that's creating imbalance so that the g is going down, so the weight is downward. That means that there has to be an internal force that's going to be in tension that's going upward. So that's the resisting load to the applied self-weight of that little partial cone. Well, here's the formula that you probably don't remember, but the volume of a cone like this is somewhat analogous to 1/2 base times height for a triangle. It turns out to be 1/3 of the base area times the height. That is not a formula that I would have expected you to commit to memory, so giving you this question on an exam would have been grossly unfair, I think, so I would not have done that. But now that you've seen it, maybe you'll remember that for this class or other classes. But again, that'd be a little bit of a trickery. The area of a triangle, of course, you should have that committed to memory. So what that means is that the P of x is going to be the weight per volume, that's our gamma, multiplied by the volume of our section. So gamma, of course, is given. That's just a number. So what that means is then that in terms of symbols that we're going to be needing, it would be gamma times the volume, which is 1/3. The base area, that's pi, times our r of x, the quantity squared. That's the radius right here for that particular segment. So that's the area, and then the height of that particular segment is our x. So now we have it. We've got our P of x. We already had our area of a function of x. And we are ready to go then. We can set up our integral then to evaluate that total displacement. So delta is equal to the integral from 0 to L of P over AE dx. And now we have expressions for P and A. E is a constant. In fact, we might want to pull that outside. We could pull out the 1 over E just to remind ourselves that that will be a constant. The length of the bar, remember to do your units conversion. As soon as you call out inches in your representation for gamma and also the area, you've already dictated then what your units will be then for the length. So that's why we got 240 in there. It was 20 feet, so 240 inches. P of x is just this. So we'll put that upstairs. We have gamma times 1/3 pi times r of x squared times x. And then we have the area downstairs. That's going to be pi times r of x, the quantity squared, dx. Well, lo and behold, in somewhat unexpected fashion, we see that actually the areas cancel. So the pi r squared, that base area, and the base area that we needed to determine the volume are both gone. And so we are left, when we pull all the constants outside of the integrand, we have gamma divided by 3e, the integral from 0 to 240 of simply x dx. So this is one of those examples where even though the geometry is not trivial, it's this circular cone, the integral that results that we have to evaluate is not very difficult at all. We can all do that one. So that's going to be gamma times x squared over 2 times 3, so 6e evaluated from 0 to 240. And that's going to be our total delta. Now remember, that's going to be in inches because we have already set up our units. Inches is inside there, inches is in there, inches is in there. So that's going to be the units that we're going to get then when we do this final calculation. So we go ahead and calculate that out, and we find then that delta is equal to 90.6 times 10 to the minus 6th inches. And we want to make sure to tell people so that there's no mistake that that's going to be downward. Incidentally, the E value that we would use it was 10,600 KSI, but the units of gamma had pounds, so when we actually punch this in, we would say 10,600,000 PSI, because gamma had the pounds per inch cubed in it. So that's another minor detail, and it's going to be somewhat frustrating if you calculate this all the way through and you're off by a factor of 1,000. So watch your units on problems like this. Let's put that inside there. Watch your units. Now, what I'm also going to do, and that finishes that example, but what we'll do is we'll assign a couple of homework problems that give you a little bit of practice, and maybe we'll do one that's not so obvious. So the homework will give you a chance to practice setting these integrals up and actually evaluating these integrals. It's one of the few times in this class where we actually get to apply some of the knowledge you learned in calculus. So you get to integrate. Huzzah! Or maybe I should say have. You have to integrate. But it's good. It's a good chance to practice some of the skills that you've learned and obviously apply some of the things that came about when you were an undergrad in your other classes to engineering practice, because it is what's going on. You do have to integrate that pointwise strain. Now that's going to be the only example that we're going to do for the case of varying strain, but they're all similar to that. It basically is ask yourself, just to summarize, which things vary. Is it P, A, or E? Then you have to set them up. Set up those values. Frequently they'll be given. I mean, we could have what's called a functionally graded material that would have an elastic modulus that varied with X. That's possible. But in any event, then you need to set up the integral and then finally evaluate. So they've all got a similar sort of flavor to them, and they're not too bad. Okay, so that's going to end our discussion about displacements with axial strain. Our next mini topic is actually related to the constitutive law, and it's one that can be a really, really big deal. And that's going to be what happens when the temperature changes. So we'll call this temperature effects. For some of you, this will be a huge topic. I suspect there are some of you taking this class right now who will spend your life looking at this. There are people in every area of industry for whom this is a huge deal. Lockheed Martin, areas of any sort of machine design. Again, this can be the difference between a component failing and a component not failing. The first thing that we want to introduce is to be able to sort of quantify what happens as the temperature changes. And most of us realize what that process is. Our experience is that when we apply heat, things expand. We don't even have to go back to our engineering career to determine that. It's just a matter of probably practical experience. Things swell up, or they grow, or they get a little bit larger when they're heated up. So what we're going to do is we're going to quantify that. So we quantify this change by using strain. And we're going to call it epsilon for right now. I'm going to write the whole thing out. Epsilon subthermal. That way, especially when we're first learning this, there won't be any ambiguity. You won't be able to make any sort of mistake. And we call this free thermal strain. Now, this word is important, and a lot of times you won't even see that written out. But what it means is that's how much strain there would be if it were free to expand. So the free aspect means that it's unrestrained by any sort of mechanical constraint. So the word free, again, it's somewhat optional, but it basically reinforces the fact that that's how much it would grow or shrink if it were completely unrestrained. And we quantify that by writing the following. We're going to call this alpha times delta T. So let's write that one more time. The free thermal strain is alpha times delta T. Now that delta T, you probably can guess what that is. So where the delta T is equal to the change in temperature. And clearly that's going to have units associated with it. It's either going to be degrees Fahrenheit or degrees Celsius. So one of those two things. Alpha is a very important parameter for us. It's another property of the material. So this is a property of the material, just like E, G, and nu. So I'll write that in. It is just like the modulus elasticity, the shear modulus, or the Poisson ratio. And it has a name that's a little bit unwieldy. It is called the coefficient of thermal expansion. And again, that's an awful lot of syllables. So almost always in the industry, everybody abbreviates it. They call it the COTE. COTE. So that is a phrasing. And maybe let's box that guy up like so. So alpha is a coefficient of thermal expansion, and it has dimensions of strain per degree temperature change. Well, strain is dimensionless, so we write that as 1. A dimensionless parameter has no dimensions associated with it, and then we will put down here the temperature change, so 1 over temp. So that is our symbol for temp. Unfortunately, T can either be time or temperature. I would probably use lowercase t for time. And this is one of the few times that we'll have to invoke temperature, so we're going to go ahead and use that. So that means the units are typically either 1 per degree centigrade or 1 per degree Fahrenheit. Those have to be called out, and they're typically given in the material data sheet. And that's wrapping up our second part for today's lecture.